everybody, Mr. Covey here, and today I want to talk about independent and dependent events, okay? And what we're really going to talk about today is when, instead of just asking the probability of one event, one thing happening, we're going to start asking the question, what's the probability of this and also this happening, okay? So we're going to run through a couple examples because there are two ways that you can have two events come together. So you can have this, and there's kind of like two different scenarios. One of them is called independent, one of them is called dependent. Okay, this first one I think won't be too bad. So hey, you have a six-sided die and a pack of playing cards. You roll the die once, you pick one card. If you don't know what cards, what the different cards are, you can always look that up online and look up. There's 52 cards, there's 4 kings, 4 queens, 4 aces, like that. So you can always look that up if you want. Okay, so what's the probability of rolling a 3 on the dice and picking a king? Well, I know the probability of rolling a 3, it's just 1 out of 6, because there's 6 possibilities and there's 1 in 3. And the probability of picking a king, if you look at all the different cards, there's 4 kings, there's a total of 52 cards. So I know the probability of picking a king. How do you bring those two probabilities together if you want to know the probability of rolling a 3 and picking a king? Well, if you think about it for a second, both of these things are pretty unlikely. And for both of them to happen would be super unlikely. So this is to be a really, really small probability. And the way you get that really, really small probability is by taking those two probabilities and multiplying. Okay, that's how you do and probability. You take the first probability and you multiply by the probability of the other thing. So let's set that in our calculator real quick. We can just use our math enter. So 1 divided by 6 times 4 divided by 52. Hit math enter. It's kind of nice to spit out your answer as a fraction. 1 out of 78. So there's a 1 in 78 chance that those two things happen. Okay? Cool. I want you to pause and give these 3 a try right here. This one, this one, this one. Okay? And unpause and we can check. Oh, I hope those weren't too bad. So let's just run through real quick. Probability of rolling a 5, that's a 1 out of 6 chance. Probability of picking a heart, there's 13 hearts in the deck. It's one of the suits. Again, you can look up a little sheet that has all the cards if you're not familiar with them. Multiply those two together, hit math enter. Rolling an even number, 3 of the 6 things are even on the dice. Picking a 3. Oops. I made a mistake. There we go. There's 4 3s and there's 52 total cards. Multiply them together, you get 1 out of 26. Last one, probability of rolling less than a 5. 4 of the 6 things on a dice are less than 5. Picking an ace, there's 4 aces out of the 52 cards. Multiply them together. Okay. Cool. If you read scenario 2, it says you got a pile of Skittles. 3 are red, 5 are orange, 7 are yellow. There's 15 total Skittles. You pick a Skittle, you put it back, and you pick a Skittle again. Actually, the probability of picking one color and then another color. Okay, so because of this and, you're going to find the probability of those two things and multiply them together. Okay, why don't you pause and give these a try? Okay, nothing weird going on there. I hope that was like pretty straightforward. I'm not even going to go over those. Just check to make sure you got those right. Okay. We're going to come back to this though because there was a key phrase in here that made this kind of work out nicely. Because now I want to look at this scenario. Well, it looks the same. You have a pile of Skittles. 3 are red, 5 are orange, 7 are yellow. You pick a Skittle. This time you don't put it back. So you grab out a Skittle and then you eat it. And then you go and grab another Skittle. Okay. Pretty similar, but that's a little different, I guess. If you think about the probability of picking a red one and then the yellow one, though, something happens here. Okay. The probability of picking a red is still 3 out of 15. But after you pick out one Skittle, Well, there's 7 Skittles left to choose that are yellow, but there's only 14 Skittles left in total because you ate. Okay, because we didn't put it back in the pile, this problem changes. Okay, that specifically, that denominator in that second fraction changes because you ate one of the Skittles. Okay. All right, set that in our calculator. 3 divided by 15 times 1/10. Notice that is a different answer than we got in 2 for the same question. Red and then yellow. In 2, we got 7 out of 75. Here we got 1/10. Those are actually close to each other if typing in the decimals, but they are different. Okay. All right, let's go through these ones. Red. Okay. And then orange. Well, if I've eaten a red one, though, then there's 1 less Skittle. So then there's only 14 to choose from. Okay. Set up in our calculator. Sorry. Get 1/14. All right, here's the last one. Picking an orange and then picking a yellow. So, whoops. Orange and then yellow. Keep in mind when you go to that yellow, there's only 14 total ones left. Okay. So I got 1/6. So should take a second and answer this question. How is this situation 3 different than the other 2 situations? I kind of mentioned it, but I want you to kind of write it out in your own words. Okay. So not replacing the Skittle makes the second denominator different. You have less total Skittles left to choose from. Something like that, I hope, is the idea here. Okay, when you don't replace it, and you just take the Skittle and eat it, it makes that second fraction a little different, that second event's probability. Okay. Overall, the probability of A and B, I just want to make sure you're completely clear, means the probability of A happening and also, all right, let's say it this way, means, yeah, well, I guess, well, let's just write it out. The probability of event A happening and also B happening. In order for this to count, both of those things have to happen. Both those things happen. I think that's clear. So we have 2 different scenarios here. And one of them is called when the 2 events are considered independent, and the other one is when the 2 events are considered. And independent is what you saw in example 1 and 2. So it was number 1 and number 2 earlier. And the reason it's called independent, and the reason the events are called independent is those 2 things, A and B, have no impact on each other. Those 2 events have no impact on each other. So if you want to know the probability of those 2 things, you just multiply them together. Those 2 events, what happens in one event has no impact on the other one. That's why they call them independent events. Okay, so if you go back here to the examples 1 and 2, what you roll on the dice and what card you pick have nothing to do with each other. What happens in the one event doesn't impact the other one. It's not like if you roll a 3, you're more likely to draw a king. They don't have anything to do with each other. They're independent events. Same with number 2. It's a little more subtle, but because you put the Skittle back, what Skittle you pick the first time doesn't matter. It's not like picking a red one makes it more or less likely to pick a yellow one. once you put it back. Okay, so those are considered independent events, and how you find the probability is you just find the probability of one of them and multiply by the probability of the other one. That's it. Okay. The other possibility was like what happened in event number 3, and we call those dependent events. So the first event, A, impacts either the numerator or denominator of event B. Okay, so if you go back to this example 3 here, if I just said what's the probability of picking yellow, you would say 7 out of 15. If I ask you what's the probability of picking red, you'd say 3 out of 15. We didn't do 3 out of 15 times 7 out of 15. We did 3 out of 15 times 7 out of 14. Because that first event, picking that red Skittle, impacted the second event. It changed the probability from 7 out of 15 to 7 out of 14 because we'd eaten one of the Skittles. That second event depends on the first one. The first one impacted the denominator, in this case, of the second one. Let me do one more example with this, and maybe it'll help too. Let's say you're doing this scenario, you're picking a Skittle, eating it, and then pick another one. What's the probability of red and then red? Okay, well, picking a red one's 3 out of 15. When you go to try to pick another red one, there's only 14 Skittles left. How many red ones are left? Well, you already ate one of them. So there's only 2 red ones left. So in this situation, the numerator and the denominator change from what you would expect. Okay, because those events are dependent. They depend on each other. Okay. So the idea here is when one event impacts the other one, we call them dependent events. And then I want you to just say this idea. You still use multiplication. It's still an AND problem, and for all AND problems, you use multiplication. But you have to be careful because of that numerator or denominator changing, or both. Okay, so you can't just look at the 2 events individually and multiply the probabilities, because the second one gets messed up by the first one, is basically the idea. Okay. And again, I want you to use that word impact in your brain. Dependent events is when one of the events impacts the other one. Okay, I'm gonna run through 3 examples for you here. So you're randomly selecting 3 cards from a playing deck. What is the probability that all 3 cards are hearts? Okay. We're going to look at this 2 different ways. First, when you replace the card before selecting the next card. And B, when you don't replace the card before selecting the next card. Okay, these are going to be very different situations. Okay, so for A, oh yeah, I should say one other thing here. I guess I'll tell you guys this. This is me being nice, but whenever you have something where they replace stuff, it makes the events independent. Because what happened the first time doesn't matter if you put the thing back. But if you have a situation where you're picking things and you don't replace it, like you eat the Skittle instead of putting it back or something, then it makes the events dependent, because once you took that card out, you kind of changed the cards that were there. Once you ate that Skittle, you changed the Skittles that were there. Okay. All right. So if you replace the card after it, then it makes these events independent events. So what's the probability of picking a heart? Well, a quarter of the cards are hearts. 13 out of the 52 cards are hearts. 1/4 of them. But if you put it back, what's the probability of picking a heart the next time? We can write out 13 out of 52 if that's making you confused. 13 out of 52 are hearts. Once you put it back, what's the probability of picking a heart again? 13 out of 52. Probability of picking a heart again? 13 out of 52. That's it. Multiply them all together. Boom, boom, boom. You get 1/64. Okay. Scenario B, though. when you don't replace the cards, well, the probability of picking the first heart is 13 out of 52. But then there's only 51 cards left. These are dependent events. At first one, they were independent. This one, they're going to be dependent. Second fractions are changing, and the third one's going to change too. How many hearts are left, though? Only 12 hearts now, because you already picked one of them. And there's only 50 cards left, and only 11 of them are hearts. So see how our fractions are changing each time there? Let's type that in our calculator. Cool. If we actually want to compare these probabilities, it probably helps to get the decimals. And I got 0.0122 for this one, and I got 0.01, excuse me, 56 for this one. So what you can see is that when you don't replace it, if you want to kind of compare these probabilities like they ask us to do, when you don't replace, it becomes less likely. In this problem, that's not always true. That kind of makes sense when you think about it, because you're not going to pick 3 hearts in a row. It's going to be less likely if you don't put those hearts back in, because there's less to choose from. Second example. Actually, you know what? I want you guys to try this one. Pause, try this one. I'll unpause, show you the answer. This one's sorry, I got to tell you what the events are. There's those events. Okay, that's what I got for that one. So the probability that you pick a $1 bill first, 20 of the 25 are a $1 bill. And then since you don't replace it, these events become dependent. The second event, the probability of it depends on the first one. So there's still 5 $100 bills, but there's only 24 bills left. Okay, so we're going to multiply those together. Oops, I guess the third one's on here. Okay. So here I just want to kind of think about it and decide whether the two events are independent or dependent. Okay, so whether the one event, what happens in that one, impacts the other one. So you got a box of granola bars with a bunch of flavors. You randomly choose a granola bar, eat it, and then choose another one. Our events are you pick a coconut one, and then you choose a cranberry almond one. Does what happens in the first one impact the second one? Well, yeah, because you ate it. So now you got a different box, right? Once you eat one of the other ones, it becomes more likely that you're going to get a different flavor. So this would be an example of two events that are dependent. What happens in the first one impacts what happens in the second. Let's look at one more example here. There are 22 novels, a bunch of different genres on the shelf. You choose a novel, put it back, and then choose another. This probability about you choose a mystery and then you choose a science fiction. Are these dependent or independent? Think about that for a second. These are totally going to be independent. Because once you put that novel back, well, then it's still up for grabs. So you didn't really change anything for that second. Thanks for watching, guys. That concludes this video. We'll do some practice with this. Thanks.